ابتهال go ahead.
السلام عليكم ورحمة الله. اليوم نرحب بكم في المحاضرة الثانية في مركز فوتون للعلوم الطبيعية والميتافيزيقيا، وبالتعاون مع مركز عبد السلام الدولي للفيزياء النظرية. المحاضرة اليوم حتكون بالإنجليزي، فعشان كده إن شاء الله كل الطرح حيكون بالإنجليزي. Ladies and gentlemen, good afternoon and evening according to your time. Welcome to the second lecture of Photon Center and for collaboration with ICTP in Italy. Today we have a special guest. We have Dr. Natasha and we have Prof. Filippo who will talk about us today in climate change. Let's first welcome with Dr. Natasha. She is the coordinator of PWF program section, and also she worked in ICTP in the fundamental physics section. So she will give us now a short introduction about herself and about ICTP Center. So welcome with Dr. Natasha.
Thank you.
Welcome.
Can I start sharing?
You want to share? Okay, let me start. Okay, you can share now.
Yes. Thank you. Good morning, everyone. Thank you for the introduction. I'm indeed co-coordinating Physics Without Frontiers. And I will take only a few minutes of your time to say a few sentences about ICTP and Physics Without Frontiers. So at ICTP, we pride ourselves on being the world-class research institute, and we like to share our model of international collaboration. Okay. ICTP is founded in 1964 by Abdus Salam, who 15 years later won Nobel Prize in Physics. And his idea was to enhance international cooperation through science. As I mentioned, at ICTP, we combined world-class research and the unique global mission of building science capacity in the developing world. ICTP is UNESCO Category 1 Institute, which means it's an integral part of UNESCO's program and budget. We are under educational institutes, one of 9 in the world. Research at ICTP is covering a number of fields in physics and mathematics. Thus, we have a high energy, cosmology, and astroparticle physics section, Earth system physics, condensed matter statistical physics, mathematics, quantitative life sciences, and science, technology, and innovation section. So research is very broad. And we also have many educational programs at ICTP taught to help fulfill the mission of ICTP. For this audience, I would mention only one, that is our program of diploma, which is a 1-year pre-PhD program, which consists of 2 semesters of basic and advanced courses, followed by a 3-month work on a thesis and defense. There is also a STEP program that you might check. So please check our web pages for more information. I don't want to take too much time today. And finally, just a word or two on Physics Without Frontiers, which is also one of those programs aimed at maybe a bit younger audiences, undergraduate, master, and PhD students, but hopefully the whole science community benefits from it. So we work to motivate, train, and teach physics and mathematics students worldwide, but we are focusing on the global south. Our idea is to help build the next generation of scientists by collaborations, by organizing all kinds of events. I'd like to say we'll have a call in November, and when we receive, we'll receive many applications for the conferences, seminars, courses, schools. Then we can discuss which ones to realize, and I invite you all to apply if you have an idea what to do. So I will finish here. I thank the speaker, and I wish you a great talk. And I hope to hear from you about your experiences and ideas for the future. Thank you.
You are welcome. Thank you very much for Dr. Natasha. I will share now my screen. So today we are welcoming with the Prof. Filippo. He's a professor and he's Emeritus Science of System at Physics section. He's also a member of Abdul Salam International Center of Theoretical Physics, ICTP in Italy, and he's the head of Earth System section. And also he's a researcher at the National Center of Atmosphere Research in Colorado. He has a degree, a PhD in atmosphere science and in Georgia Institute of Technology in Atlanta, USA. Also, he has a great research experimentation at global and regional climate modeling, also in climate change impact and climate processing. Our professor today, he achieved several prizes, especially he is one of the brilliant of field of regional climate change, and also he is working also as a part of the team award in 2007 for Nobel Prize. He is also have a global in meteorology and atmosphere physics in Stanford University. And he's also working at Alexander von Humboldt in the middle by European Geoscience Union. So welcome today with our professor. And before we start, Professor, we will have a group picture with all the participants. So after that, you can have the mic to start your meeting. So please prepare yourself, everyone. Please open your camera and be ready to take a group picture. يا ريت كلكم تفتحوا الكاميرات عشان ناخد صورة سريعة ونبدأ. لما انت تكون جاهز يا دكتور أبو بكر قول لنا.
اوكي حنبدأ ناخذ الصورة الآن. We will check the photo now. Okay, I'm done. Thank you all.
Please close all your camera now and let's welcome with Dr. Prof. Filippo. Ala, you can share the screen now.
Thanks. So
I will share
Sarah,
the screen.
thank you very much for inviting me to give this lecture. Okay, somebody's sharing the screen, I think, for me to move the slides.
Yes, Ala, preparing to the sharing.
Go up. One more. Okay. So again, this is the first slide. Again, I thank Natasha for inviting me to give this lecture. And of course, I thank all of you for being here. As you've seen, I was the former head of the Earth System Physics section until 2024, until last year. Then I technically retired, but I'm emeritus at ICTP. We used to organize many workshops and still organize many workshops on climate change issues. That's my area of expertise. In particular, I'm a climate modeler. I've worked for about 35 years on climate modeling, especially regional climate modeling. So I will give you today an introductory talk about climate change, looking at scientific evidence, the main risks, and very briefly on some mitigation options. So if you can go to the next slide. Yeah, this one. I usually start with a slide like this just to remind you that we are really in the middle of a quite important climate emergency. Sometimes in the news there are other things because, of course, many things happen in the world, but actually, especially the last years have been incredibly anomalous from the climate point of view. Many of you may know that 2023 and 2024 have been by far the warmest years on record since global measurements are taken, so since the beginning of last century, partly because of a important El Nino that developed in 2023 and peaked in at the end of December 23 and beginning of January 24. Then now we move to the La Nina, but even though we move to La Nina, where much of the Pacific is relatively cool, also 2025 looks like a very warm year. So global warming is definitely still there. You see here some of the really big events that have happened in the last few years. In Europe, we had record heat waves in 2019, 2022, 2023. Also 24 was very, very hot. These are heat waves that have a return period of 1,000 years, more or less, and now they happen almost every year. So it means really that things are changing. We had a huge drought in 2022. This was the worst drought that Europe had in the last 500 years. You may remember some of the big floods that happened in the last few years. Pakistan, you remember the flood in Derna, the city of Libya, and where there was an overflow from a dam. And there are reports that maybe more than 10,000 people actually died. Last year in Valencia, in Spain, we had a big, big flood. And in the bottom to the left, you see something that people have not talked about, but was an amazing anomaly. In March of 2022, in Antarctica, we had an anomaly of more than 40 degrees that you see there. So the temperatures, instead of being like minus 65, they were only minus 20 or something like this. And at the same time, we had a 25-degree anomaly in the Arctic, and this had never happened before. If you go to the next slide, the next slide, this shows a very interesting satellite picture because it's also another unprecedented event. On 6th October 2024, we actually had 3 hurricanes in the Atlantic, and this had never happened since in the month of October. In particular, the Hurricane Milton was the strongest ever recorded hurricane. And Hurricane Kirk was very interesting hurricane because it actually, instead of after moving towards the US, then it went to the north and then it moved towards Europe, which is very anomalous. And it actually hit Northern Europe and Central Europe, doing a lot of damage. And the reason for going so much north and so being pushed by the westerlies was that the waters of the Northern Atlantic were very, very warm. And then the Hurricane Leslie. So I would say that now every year there are new records, every year there are new unprecedented events. So climate change, unfortunately, is here and it's affecting our lives. If you go to the next slide, this slide is there just to remind you that when we talk about climate, we don't just talk about the weather. We don't just talk about is it raining, is it hot, is it cold, and so on. But we talk about a very complex system It is composed of several components like the atmosphere, the oceans, the cryosphere, so the ice, the biosphere, and since the beginning of the Industrial Revolution, we can add the human components, whom we know now are affecting the global climate, and that I call anthroposphere. So all these components interact with each other. So if you modify one of them, so if you change the atmosphere, you change the whole system. If you change the oceans, you modify the whole system, and the same with the cryosphere. So touching one of these components implies touching the entire climate system. And the other message from this slide is that this is a very complex system that can react to big perturbations in ways that are really very difficult to predict. If you go to the next slide, this is another basic concept that I think you should all know, because it's a concept at the basis of the global warming issue, and it's the concept of the greenhouse effect. I'm sure many of you know about this, but let me just remind you what is the greenhouse effect and why it is important. Why are we talking about this? You know that the engine of the climate system is the sun, is the radiation coming from the sun. Our clear atmosphere, so without clouds, is quite transparent to the sun's radiation. Not much of it is reflected or absorbed by the atmosphere. So most of the sun radiation hits the surface and warms the surface. The surface then needs to have some mechanisms to cool down. One of these mechanisms is the emission of infrared radiation. So radiation that is at wavelengths longer than the visible radiation. We cannot see infrared radiation unless we have special tools. So if the atmosphere was not there, this radiation would be emitted from the surface and we would go to space. And if we did not have the atmosphere, the equilibrium between the incoming solar and absorbed solar, some of the solar, of course, is reflected by the surface. And the outgoing infrared radiation would lead to temperatures that are would be about 30 degrees lower than today, so quite cold. So not very good for life to develop on the planet. But we do have an atmosphere, and the atmosphere has some gases that are called greenhouse gases. You see the list of the main greenhouse gases. Water vapor is a big greenhouse gas. Carbon dioxide, ozone is another greenhouse gas, methane, nitrous oxide, and chlorofluorocarbons. These are the main greenhouse gases. The most important that we care about are, in this context, are carbon dioxide, CO2, and methane, CH4. These gases have a property of absorbing some of the infrared radiation that is emitted from the surface. And they also re-emit it because they also have to cool off, but they emit it in all directions. So they emit it to space, but also part of it they re-emit towards the surface. In this way, they trap some of the infrared radiation from the surface, and in this process, they heat the surface and the lower atmosphere, and increase the temperature to the values that we see today. So why they're called greenhouse? Because greenhouse gases, because it's the same process as the glasses in a greenhouse. They let solar radiation through, but they don't let the infrared radiation back out. So in general, these greenhouse gases are good for the atmosphere. The problem is, if you go to the next slide, that some of these greenhouse gases are, the concentration of some of these greenhouse gases is increasing very fast. In this plot to the left, you see measurements of the carbon dioxide concentrations at Mauna Loa, Hawaii, but carbon dioxide is very well mixed in the atmosphere. So carbon dioxide over Sudan is mostly the same as over Mauna Loa, Hawaii. You see that there has been a big increase. This plot, we cannot see the bottom end, but at least I cannot see it. But it goes from the 50s to today. Pre-industrial values of carbon dioxide concentrations are around 270, 280 parts per million. Today we have about 420 parts per million. So that's an increase of about 50% in 120 years, which is something that our planet has never seen before. And this you can see from the plot to the right. In this plot to the right, if you go to the upper panel, you see the reconstruction of carbon dioxide concentrations in the last 10,000 years. Again, you cannot see, at least I cannot see the bottom of the screen, but there is a temporal scale. It goes back 10,000. You see quite flat around 275 to 80, and then this big sudden increase in the last 100 years. So you see already this is telling us that it's a very anomalous behavior. Methane is more than doubled compared to carbon dioxide. Methane is an important greenhouse gas because per molecule is much stronger than carbon dioxide, about 30 times more efficient. But there is much less. Carbon dioxide is measured in parts per million. Methane is measured in parts per billion. So it's 1,000 times less abundant, let's say 100 times. So you see that the concentration has gone from 700, 750 to more than 1,700. So that's more than double. And also nitrous oxide. Today we know for sure that the increase in carbon dioxide that you see in the last 100 years is mostly due to the use of fossil fuels, because carbon dioxide is produced by combustion. So every time you burn something, you produce carbon dioxide. So the use of petrol, natural gas, or coal is the main responsible of this increase in CO2. The increase in methane is due to losses of methane when this is taken from the soil. For example, when they do fracking or other ways of taking methane, but also it's produced by the digestions of herbivores. So it's been attributed to intensive farming. I don't know if you have this in Sudan, but in Europe, in the US, in China, in many countries, there is very intensive farming of cows, pigs, and other animals that are eaten. So this is what one of the main causes that causes the increase in methane. So if the concentration of these greenhouse gases increases, we should expect a warming of the global climate. If we go to the next slide. Oh, okay, before we go to the warming, something very important is that the greenhouse effect due to the increasing greenhouse effect due to the increasing concentration, say, of carbon dioxide, also triggers some of what we call feedback processes. These are processes that feed on themselves. So once they get going, they keep going. I just want to mention two of them. One is the water vapor feedback mechanism. As you know, because of the Clausius-Clapeyron law, a warmer atmosphere can contain more water vapor. But water vapor is itself a greenhouse gas. So if you have warmer atmosphere, you have more water vapor, more greenhouse effect, warmer atmosphere, more water vapor, more greenhouse effect. So it's a loop, because you also have more evaporation from the oceans. You have a loop, and this tends to amplify the global warming. Another amplifying effect is the so-called ice albedo feedback mechanism, very important for the polar regions, for the high elevation regions where there is snow. As you know, the ice and snow reflect a lot of the solar radiation, but if you have a warming atmosphere, you have melting of the ice and snow, so you expose the the underlying ground, which is darker, so it absorbs more solar radiation, so it warms more, melts more ice, exposes more dark soil, absorb more solar radiation, warms, melt. It's a feedback process that tends to amplify the warming. I mentioned these feedback processes because they're responsible for more than half of the warming that I will show. In fact, they are even more important than the direct greenhouse effect itself. This is very important to remember. Now, if you go to the next slide, this is the global temperatures measured by University of Berkeley. There are several labs doing this. Of course, there is not a yes. Of course, there is not a thermometer that measures the temperature of the Earth, but this is estimated from data from tens of thousands of observing stations in the whole world, satellite data, buoy data, ships, all sorts of data. They're put together by these labs, and you get an estimate of the temperature of the Earth. Now, these are temperature anomalies compared to a reference period, which is the end of the 20th century. And you see that we have undergone a warming of about 1.25 degrees in the last 120 years. And as I mentioned, the last decade has been the warmest on record, and the last 2 years, the warmest on record. Now, you also see some oscillations. See, it's not just going up. These oscillations are due to natural variability. So if, for example, if you have an El Nino year, El Nino is a natural phenomenon. Much of the Pacific is relatively warm, so the curve has an upward kink. If you have a La Nina year, then you have a downward kink. So you get these little oscillations. But when we talk about climate, we talk about long-term trends, and in the long term, there is definitely a warming. Now, just to put this 1.25 degrees in 120 years in the context, if you go to the next slide, this is a reconstruction of global temperatures in the last 2,000 years. See, 2000 is present day, essentially, and then all the way back to zero. And this is from a Nature Geoscience paper. It's the result of a big European project called PGS2K. No, European, international project. And several labs reconstructed global temperatures. There are many ways of doing it, from ice cores, other indicators, pollens, and so on. So you see that the temperature has been fairly stable between 2,000 years ago and 1,000 years ago, the so-called medieval warm period. But as you can see, it was not that warm at the global level. Then there was a descent, a decrease in temperatures in the 1600 to 15 to 1700. We had the so-called Little Ice Age. You see relatively cool temperatures, but this is part, I will show, of a general cooling trends on the long term. But then you see in the last 100 years, there's one point something degree. So as you can see, this is something that is very anomalous. Our atmosphere has not seen this at least in the last 2,000 years, but I will show you at least in the last 10,000 years. And today we know for sure that, so you see that this is a big 1.25 degrees in 100 years globally is something very fast and something very anomalous. So that's a big warming at the global scale. And today we know for sure that this warming is due for the most part to the increase in greenhouse gas concentrations due to fossil fuel emissions, so due to human activities. Also, this conclusion in the last IPCC report was given as essentially certain. So we know the concentration of greenhouse gases is increasing. We know it's due to human activities, mostly fossil fuel burning. And we know that this is causing the global warming that we are actually seeing today for sure. For all these things, the word unequivocal is used in the IPCC reports. Now, if you go to the next slide, these are the trends for Africa from 1980 to 2015. On the left, you can see temperature trends, and on the right, you can see precipitation trends. Sudan, you can, this is taken from the IPCC report where they divided Africa into 5 broad regions. Sudan belongs, I would say, to the northeastern region. But you can see that the area where you live, the Eastern Africa, is one that is warming at the fastest rate. I'm not really sure why this is. I don't know if somebody has made a specific study about this, but of course there is some spatial variability that is inherent to the climate system. But the Mediterranean is in general a hotspot, so where the warming is particularly strong. For example, Italy is warming at twice the rate of the global average. I think Eastern Africa is also warming at a rate that is more than twice the global warming rate, because you had in 35 years more than half degree warming. So that's per decade. So we're talking about 1.5 only in 35 years. So wow, boy, that's big warming that is happening in your region. To the right, you can see the precipitation trends. Blue is positive and yellow is negative. So actually the news is not so bad in this case, because in the Sahel you see maybe a positive precipitation trend. Now precipitation can have positive and negative trends because it depends on changes in the global circulation. You see warming almost everywhere, except this small region over Southern Africa, but precipitation is more mixed, and this is because the changes in local and global circulation regimes. But you see some fairly strong decreases in the Horn of Africa, in Eastern Africa, some areas of Central Africa and Madagascar. Now you can go to the next slide. One of the effects of global warming, maybe this is not so important for Sudan. I don't know if you know, I don't, probably in Sudan there's no snow, I'm pretty sure. But an important effect in mid-latitudes and high elevation regions is the melting of glaciers. And this is happening pretty much everywhere. For example, over the Alps, all the Alps where I live, all the alpine glaciers are actually in a recession phase, and many of them are doomed to disappear by the end of this century. One important aspect of glacier melting is that glaciers are our main reservoirs of water, globally speaking. For example, much of Asia depends on the water from the water towers of the Himalayas. And so if glaciers disappear or decrease, it means we have less water, less fresh water. And of course, as you know much better than me, today we don't have enough water for everyone, and the water is very, it's not well distributed. Some countries have too much, some countries, maybe Sudan, don't have enough. So water, I think, would be a big issue in this century. If you go to the next slide, of course, the water that melts from the glaciers goes into the ocean, and so it increases the level of the ocean. And also the ocean waters is warming, and as it warms, it also expands, not much, but there is a lot of ocean, so contributes to to the sea level rise. Here, see measurements of sea level rise at a global scale, and you see that it's increasing quite fast, actually, also in this case. The increase is about 20 centimeters since the beginning of the last century. But actually, some projections tell us that sea level could increase by up to 1 meter by 2100. This would be very, very important for coastal regions, also coastal regions of Africa, because of course many cities, maybe big cities in Africa, are located over the coasts, and this would be strongly affected by sea level rise, with more coastal floods, intrusion of saline water, and so on. Go to the next slide, please. Another important issue that is quite relevant also for Sudan and also for Africa is what we call the intensification of the hydrologic cycle. As I mentioned before, a warmer atmosphere, of course, has more energy because of the higher temperatures, and also has more water vapor because of the Clausius-Clapeyron equation and the increase of evaporation from the oceans. So if you have more energy and you have more water vapor, when it rains, it tends to rain, the intensity of rain is higher. This means that you increase the risk of floods. At the same time, this takes a bit long to explain, so we can do it offline. If somebody interested, send me an email. It takes more time to trigger the rain event. So the periods between the rain events, the dry periods, increase in length. In other words, it tends to rain more intensely but less frequently. So less frequent rain event, but more intense event. And with the heat waves, this increases, since you have longer dry periods, this tends to increase the risk of droughts. So paradoxically, you have an increase in the risk of flood, but also an increase in the risk of drought. You have long, dry, warm periods, but then when it rains, it tends to rain very, very strong. If you go to the next slide, this is just to show you that we see positive trends in extreme events pretty much everywhere. This is a figure from the IPCC report. You see that all regions of the globe have been represented by hexagons. I think Sudan is in the East Asia hexagon that you see there. You see East Africa, sorry. You see Africa there, and the Mediterranean and Europe. The top panel shows the trends in, these are observed trends in heat waves, and you see that pretty much heat waves, and if you have a color, it means that the trend is statistically significant at the 95% confidence level, which for extreme events, so these are rare events by definition. To get statistical significance, it means you need to have a strong trend. You see heat waves are increasing pretty much everywhere in a significant way. The middle panel is shows the trends in heavy precipitation events. And you see the green shows you areas where you have a statistically significant trend in heavy precipitation events. So you see many areas of Asia are seeing statistically significant positive trends. Some areas of Southern Africa, of North America and South America, and Northern Europe as well. And again, these are not easy trends to detect. So the fact that they're statistically significant means that the trends are very strong. And you don't see any negative heavy precipitation trends. So you see this effect of when it rains, it tends to rain more intense. And then you see in the bottom panel, these are trends in ecological and agricultural drought. So also in this case, except for Australia, where you see a little green green hexagon. But mostly you have the increase in drought, especially in the Mediterranean. Mediterranean is getting drier and much hotter. But you see also Northern Africa, the same, and almost the whole African continent is actually seeing an increase in drought. So I think drought, again, as I said, water is going to be a big, big issue for the world in general, but I would say for Africa in particular. Now you can go to the next slide. This slide shows you the number of what are called the catastrophic events. These are from the Munich insurance company. Of course, they're very interested in these events. You see here 4 types of events. The red is geophysical events, meaning earthquakes. Fortunately, as you can see, the number of earthquakes or damaging earthquakes has not increased in time. But the others are meteoclimatic events. So storm, flood, fires, droughts, and so on. And you see a big increase. In the 80s, we had about 200 catastrophic events per year. Now we have about, well, now this is 218, we have about 800. I've seen somewhere a plot where in 2020-21, we had even more than 1,000 events, catastrophic events, big droughts, big floods, big fires, things like that, big storms that cause a lot of damage or a lot of deaths. This means that in 40 years, we had an increase of a factor of 4. So a doubling time every 20 years, which is really, really very fast increase of this extreme event. So this is another big risk also for Africa. Now you can go to the next slide. This slide kind of summarizes the main climate change indicators: carbon dioxide, global temperature, increase in catastrophic events, sea level. So you've already seen these plots, but I put them all together here because they show us that all these curves in common have the characteristic that not only they go up, but they go up in a non-linear way. So it's a positive second derivative, which means that climate change is actually accelerating. But this is really not good news in terms of the effects of climate change. The situation is definitely not very good from the climate viewpoint. And this, I mean, there are some good indicators as I'll show you, but at the moment we're still in a sort of very fast rising curve in terms of climate change indicators. Now we can go to the next slide. These are the projections for how global warming might go in the future. Let me just tell you that this would require a whole lecture, but that climate cannot be predicted in the way we predict the weather. We cannot know what climate will be in 2075 to 2085 or so on, because the system is chaotic, is nonlinear, because we don't know how the emissions of greenhouse gases is going to evolve, or if something else is going to happen. So we cannot predict climate. What we can do, we can have some reasonable hypothesis of how greenhouse gases might change in the future. We put this into our models and we see what our models tell us about how climate in the future might be. So these are not climate predictions, these are actually climate, we call them projections or climate scenarios. Now you see here the main scenarios in the last IPCC report. These are global temperature anomalies compared to pre-industrial values. And there are 5 scenarios with these names. The top 2, SSP 1, 2.6, and 1.9, are scenarios where the global warming stabilizes to below 2 degrees compared to pre-industrial temperatures. So you may think of these 2 scenarios as being scenarios compliant with the Paris Agreement, with the objectives of the Paris Agreement. the Paris Agreement was an agreement that was made in 2015. Unfortunately, it's not a binding agreement, but was an agreement to keep temperature change to below global temperature anomaly change to below less than 2 degrees compared to pre-industrial values. We already are 1.25 above pre-industrial, which means that we are not far from breaking the Paris Agreement target, only 0.75 left. Then you see higher scenarios. The worst scenarios is the SSP 5, 8.5. This is sometimes called the business as usual scenario, in which a global climate might warm by 4 to 5 degrees by 2100, which really would be, I will show you something very, very, very anomalous. If you go to the next slide. This is a slide just to tell you that global warming to the left and changes in precipitation to the right are not homogeneous, but there are areas that are more sensitive. We call them hotspots. And you see that based on temperature, Mediterranean and Northern Africa and Eastern Africa is a big hotspot. In fact, you saw also in the observations that there was a big warming, also in Sudan. So we are both in the same climate change hotspot, where we expect much higher temperatures. In the Mediterranean, much less precipitation. You can see on the right, the brown. Maybe in the Sahel region, you can see actually an increase in precipitation. Another big hotspot is the Arctic. It's far away from you, but this will have global effects on the global climate. So it might also affect climate in Sudan. Now, if you go to the next slide, these are projections for Africa. I've taken this from the IPCC 2021 report. You see in the top, these are changes at 1.5 degree global warming, 2.5 degree global warming, and 3 degree global warming, okay? So even exceeding the Paris Agreement target. So you see here, increase in temperature, and again, one of the hotspots is in Northern Africa. The number of days above 35 degrees, so very, very hot days. Precipitation you see over the Sahel. Some good news is that over the Sahel, you have an increase in precipitation, but also an increase in heavy precipitation. Much of this increase is actually associated with heavy precipitation. So there is a big increase in the risk of flood. And in the next one, you can see a big increase, definitely a big increase in the risk of drought. This is a drought measured by the 6-month precipitation intensity index. So the precipitation anomaly on a 6-month basis. So you see, unfortunately, that over your region, you see an increase of risk due to dry and wet climate events, as well as heat waves. This is not to give you some bad news, but unfortunately, Mediterranean and Africa are two very vulnerable regions about climate change. If you go to the next slide, maybe I will skip this one. This will take too much time to go directly to the next one. I just want to put all the data that I've given you in the context of what has happened in the past. What you see here is our reconstruction. This is the most, the best sort of reconstruction of temperature anomalies in the last 11,000 years, a period that we call the Holocene. You know that in the last 2 million years, the climate has oscillated between glacial periods and interglacial periods because of some small variations of the Earth's orbit. So this is a natural phenomenon. The peak of the last glacial period was about 20,000 years ago. Then starting 20,000 years ago, the temperatures started increasing. At about, you can see here, about 10,000 years ago, we started the peak of the last interglacial, so of the Holocene. Then temperatures have been very stable for about 500 years, 5,000 years. And about 5,000 years ago, you see, we started the slow descent towards the next ice age, which we would reach in about, I don't know, maybe 20, 30,000 years. So not something that we need to worry about. But if you go to the next slide, now you see the situation today. Actually, this paper is from 2013, so today would be even worse. So you see that this 1.2 degree in 100 years is very, very anomalous. It's something that our planet hasn't seen, at least in the last 10,000 years. I don't think this has ever happened in all of the warm periods of the last 2 million years. Maybe in some cold periods there were very fast events because of the ice feedback, which can be very fast, like this one, but not in the cold periods. So we're already seeing something very anomalous. If you go to the next slide, this is what would happen if we could stay within the Paris Agreement. This is 2 degrees global warming compared to pre-industrial. So you can see, even in the best case, hoping that we can stay within the objectives of the Paris Agreement, you can see that we would give the climate system a very big perturbation. And you remember from the beginning of my talk, the climate system is a very complex, chaotic system. So it's unclear what this might cause, giving it a perturbation that is so strong. But if you go to the next slide, this is the business as usual. So this would be really something that would be very difficult for everyone, because it would mean that it's a complete change in the climate system. It's a perturbation we have never seen. We would live, we or whoever is there, your children probably will make it there, our children. We live in a different planet from the climate viewpoint. What does it mean that some areas that today may be fertile could become deserts, or vice versa? Some areas may get big changes in extreme events. It doesn't mean that the planet will become not habitable anymore, but it will become much more hostile for human civilization. And whether we can survive well a perturbation like this, I think it's highly debatable. That's why in Paris we said we should not break this objective, because this threshold of 2 degrees, because what happens when you go past 2 degrees, also you have some what we call tipping points, some processes that become uncontrollable. For example, the melting of the Greenland ice, and if the melting of the Greenland ice accelerates, you can have several meters of sea level rise, and this would be really something very, very bad. So we need to try to stay within the Paris Agreement. Go to the next slide. Now, what does that mean? In Paris, it was essentially decided to stay below the danger threshold, which is, again, 2 degrees global warming compared to pre-industrial, remember, not compared to today. So only 0.7 compared to today. I think we already reached the 1.5. I think 2023 and 2024 were already above 1.5 degrees warming compared to pre-industrial. So we are already past the very strict, stringent, let's say, objective of the Paris Agreement. Now, to do this, we need to decrease emissions of greenhouse gases, essentially going to zero net emissions by 2050. Not zero emissions, sorry, here I didn't write it, but not zero emissions, but zero net emissions. So if you emit something, you have to take something back. Now the CO2, for example, is emitted by burning, but also there is an exchange with photosynthesis and respiration, and exchange with the oceans. Now let's see how we are doing. You can go to the next slide. These are the emission trends. As you see, we had the big increase, then things were kind of leveling off at the end of 2017, 18. We were supposed to reach the peak in 2020 and start decreasing. You see this decreasing kink 2020, 2021, that's the COVID. And there was a lockdown, but after 2020, in 2021, we started rising again. So unfortunately, in the Paris Agreement, it was stated that we should peak in 2020 and then go down all the way to zero at 2050, but it doesn't look like this is happening now, unfortunately. So we need to be more active on the decrease in emissions. If you go to the next slide, now this is part of the problem. These are the carbon dioxide emissions by country. And as you can see, in Europe and United States, actually the emissions are actually decreasing since 2000 or something like that. This because of the so-called green economy, you have more renewables, but also because many of the factories were moved to Asia. So in Asia, in China, you see this big increase. In India, you see this big increase. But also you see the black line. This is other countries, so this includes also Africa. And you see this big increasing trend. So I think it's very, very, very important that Africa has its development. Of course, Africa has to develop economically and the well-being of the people, but this has to be done. I think it's very important that it is done within the context of the green economy. You can go to the next slide. This gives you some kind of good news, I think, because this is, for example, you see that in China, now this gives you consumption versus production. Tells you that in China, there is a lot of production of energy, but not all is used in China. A lot of the energy is actually used in the US and in Europe. It's sold to US and Europe, for example, coal or gas or oil. But you see in China, you have less consumption than production. But you see very important that essentially the emissions are leveling off in China. China is the biggest emitter, but they're implementing a lot of green energy policies. They're the biggest producers in renewable energy, the biggest producers in electric cars, in the use of photovoltaic energy, wind energy, hydropower energy, and so on. So there are good signs. Also in India, you see that things maybe are slowing down, so that's also good news. And of course, we already said that in Europe and US, the emissions are decreasing. So it's very important that the poorer countries develop, but we develop within the context of a green economy. So there is this whole issue of the fund for climate for the poorer countries that is debated every year. This, of course, requires big funding, and not many countries are willing to give this to the poorer ones. So there is a big issue of transfer of funding from the richer countries to the poorer countries to allow them to develop in a green economy context. Now, if you go to the next slide, this shows you what I mean by, in Italy, we call it ecological transition. The biggest thing is the decarbonization of the energy system. So going from the use of fossil fuels to use of renewable energy, and especially energy efficiency. Today, we waste about 60% of the total energy that is produced. So we need to reduce this waste. But then we had I added here reduction of food waste and intensive farming, because this is related to the emissions of methane, which are very important. And reforestation, because the forests absorb carbon dioxide with photosynthesis. So now we are in the process actually of deforestation. Actually, unfortunately, also in Africa, there's a lot of deforestation, but especially in Asia and in South America. So we have to at least stop that. Deforestation today contributes about 11% of the total CO2 equivalent emissions. Circular economy, so the reuse of resources, and zero-kilometer economy, meaning try to use local products, because if you have to carry products for tens of thousands of kilometers, this of course implies emitting carbon dioxide. Now you can go to the next slide. And this is just to show you that this is the share of electricity production from renewable energies. So the darker colors means a big share. And you see that in Africa today, actually, renewable energy constitutes a big portion. In many countries, more than 50% of the energy is produced by renewable energy. Even Sudan, okay, but let's see, there is a big production. Maybe this is hydropower. Maybe somebody knows what type of renewable energy it is, but
Solar cells.
sorry?
Solar cells.
Solar cells, okay. That's good. See some countries in Europe, Spain, for example, Italy also is not doing so bad. Germany, mostly wind energy. The Nordic countries, mostly wind energy. So I think for Africa, it's definitely possible to give energy to everyone, but from clean sources and not from the use of fossil fuels. Now you can go to the next slide. I'm almost finished. I see that I passed my time. Okay, I will shorten all this just to tell you that CO2 has a actually, I'm not doing too bad in terms of time. We start at 11. Okay, so let me just go through this because I think this is an important message. Now, one important issue that not many people understand is that CO2 has a very long lifetime in the atmosphere, carbon dioxide. On average, after all the exchanges with the ocean, with the forests, and so on average, the molecules of CO2 reside in the atmosphere for, let's say, order of 100 years, okay? So what matters are not the emissions on a given time, but the emissions over a long period of time, because what the concentration of CO2 today depends on the emissions of the previous 50 to 100 years, okay? So I can go to zero emission today, but then if I emitted a lot in the last 50 years, then that CO2 has actually built up. Now, there is a relationship that had, so what matters are cumulative emissions, okay, cumulative over time, because of this long residence time. Now, people have found a relationship between cumulative emissions over time of CO2 and global warming. And in particular, this has been found both in the past, in the data from the past, and in the model projections for the future. And it has been found that 1,000 gigatons of cumulative CO2 emissions corresponds to about half-degree global warming. Today, we emit something like 40 gigatons per year. So you can just do a quick calculation from this and say, if we keep emitting at this rate, how many years we take to break the Paris Agreement target, and you will find that in about 30, 40 years, if things don't change, we will go there. We will already pass the Paris Agreement target. So, but anyways, if you go to the next slide, this is a graph that shows you what it would take to go to the Paris, to stay within the Paris Agreement target. In the Paris Agreement, it was decided, it was The idea was to peak in 2020 and then go to zero in 2025. So you see emissions in the y-axis and time in the x-axis. This is my own figure, so it's just to show you the concept, okay? So it goes from about 35 gigatons of CO2 to about zero. What matters, as I told you, is not the zero emission. Of course, the zero emission 2050 matters, but it's all the cumulative emissions in this period of time. So the area underneath this curve, the area that I've indicated with green bars. And let's say that this is you can use that little formula that I showed you, 1,000 cumulative gigaton emissions equals half degree. To stay within 1.5 degrees, but we are already past this. But anyways, when I did this some years ago, the virtuous trajectory was a reduction of 3% per year of global emissions. Anyways, this is, let's say, what it would take to stay within the Paris Agreement. If you go to the next slide, it shows you what happens if we don't do anything for a number of years, like we're doing now, and then we go still in a linear way to 2050. Now, the area underneath the curve is the green curve plus the red curve, the red area. So we go to zero emission 2050, but we exceed the Paris Agreement target because the total area is above the one that is necessary to stay within the target, because what matters is the area, not the final emission value. And this tells you why. So if you go to the next slide, it shows you that if we keep increasing emissions in the next years, then we cannot go to zero in 2050, but we have to go to zero much earlier. So the more we wait to implement some emission reduction policies, the stronger they have to be later, and more difficult it will be to stay below the danger threshold. So this is why everybody says we need to act soon. There is an urgency. We cannot wait another 20 years and hope that somebody will find some miraculous energy source or something like that. I think this way you can go to the next. I think this was the last slide. So I'm going to thank you for your attention. I tried to give you a broad overview of the climate change issue, the risks associated with it. Let me summarize all this with telling you that climate change is real, is happening. Global warming and all the effects on the climate system is real, is happening. We have seen the scientific evidence that today leads the scientific community to say that climate change is unequivocable, and is also unequivocal that is due to human activities, especially fossil fuel emissions. It has some effects on the climate system, like the increase in sea level rise, increase in devastating meteoclimatic events, loss of water, that have big effects on human society. And these effects can be very bad if the climate change if the global warming is quite high. In the Paris Agreement, they identified a target of 2 degrees compared to pre-industrial values. Unfortunately, we are not very far. And people think if you pass this target, you start some accelerating effects, like the melting of the Greenland ice. And the impacts of climate change will be too bad to be dealt with adaptation options. So we really need to act fast in what we call the ecological transition. In the richer countries, it's a transition going from one energy system to another. The poorer countries is development, but not using fossil fuels, but using alternative renewable energy. It's something that I see is already happening, and I hope it keeps happening more and more. So this is my final message, and I thank you very much for your attention. I think we have a bit of time for some questions if you want. I don't know if somebody's gonna take over at this
Thank you very much, Prof. Filippo, for this
point.
interesting lecture. And I hope really all the people around the world as students and research work very hard to save our planet. So now I will give the chance for who raised his hand. Yasser Ali, you can open your mic.
Thank you, Professor Filippo, for this enriching and insightful lecture about climate change. If I like to describe the lecture, it was an analysis for the situation of climate change. What have we do, or should we do to embrace the model that has been, initiated in Europe, in Spain, in Italy, whatever the places, and try and replicate the model in Africa, or let's be specific, in Sudan. So we are talking about analysis of the climate change, but what we should do. Me myself, I'm working in a National Energy Research Center in Sudan. We are, embracing the indices that put by the UNFCCC, the indices of which is the nationally determined for the CO2 emissions. So what should we do as you as expert in climate modeling or climate change modeling, specifically just talk? I thank you so much.
Yeah. Okay. First of all, let me tell you that it's not that Europe and US are very virtuous. Huh? One of the reasons why the emissions are going down in Europe and US is because all the factories have been moved out. So technically speaking, the goods are produced in China, so the emissions are in China, but then the Europeans and the Americans buy the goods. So that's the difference between consumption and that's why I showed you that figure, production and consumption. I think the most important aspect is the energy aspect. You work in an energy institute or organization. Again, the development of Africa has to develop. I mean, Africa has many. I've traveled through Africa a lot, gave many lectures in different countries, and poverty has to be eradicated, and Africa needs to develop and reach better conditions for everyone. But this has to be done within a context, not within a context of using an economy based on use of fossil fuels. So I think what you're doing, I think it's great in the sense of using, I think solar, was said, photovoltaics. Just keep going in this direction. Try to electrify as much as possible your systems, because electric engines are much more efficient than internal combustion engines. One of the reasons why we waste so much energy is because of internal combustion. And in a car, if you take an internal combustion car, a normal car, let's say, and an electric car, the electric car is much more efficient in terms of energy loss. So already switching to electric heating, electric whatever. But of course, I'm not familiar with the situation in Sudan, and I don't know how easy it is to do this. But electrify all the systems and produce the electricity through, I think solar in your case would be the best choice. I don't know if you have hydropower generation in Sudan.
We do have hydropower in some dams in like Marawi Dam or some river inside Sudan, and this is like a Greater Nile. Also, we have dams for generating hydro.
In the southern Sudan, there's some dams. No, there is an area that floods. No?
Yeah, we have a floods. Yeah, in specific area. There is a specific movement towards or migration toward renewable energy overall, like hydrogen and waste to energy also, not just only solar power, solar panels or solar technologies. So we
Yeah,
have
you're
to
actually producing hydrogen. Is that correct?
uh, yeah, we working on a pilot project in our center to produce like hydrogen energy waste from waste biomass and water electrolysis, but we don't want it to compete with the available sources for human being, you know. So we are targeting the wastewater treatment, the water from the sea to produce the hydrogen from it in a
Okay.
single state.
So I think all this is great. Just I would say continue and do more. I think the transition has to happen without use of force, but I think this will happen. I just hope that for Africa it happens fast, so that you can develop, but in a more intelligent way than we did.
Thank you so much, Professor.
Mohammed has a question, I think.
Mohammed, open your mic, introduce yourself first, and start with your question.
Hello, Professor. My name is Mohammed Sir Al-Hatim, a student in the physics department in the University of Khartoum. My question is, you have already talked about a loop with water vapor, and my question is about the reservoirs, the huge reservoirs of carbon that is trapped under ice of ancient organic material. And I do believe that there is a huge reservoir of carbon that is going to be released. And so we're going to have another loop, maybe a bigger loop of cause and effect. And do you believe that this amount of carbon that is frozen, if released, can lead us to a point of no return, a point where we cannot even control carbon emissions anymore?
Okay, that's a good question. Actually, when I showed that slide, there were 4 loops. I only talked about the top 2 because I didn't want to use too much time. But the third one, I think, was exactly what you're talking about. Just for the other people, let me talk a bit more about this. I think what Mohammed was talking about was related to the problem of permafrost. Permafrost is frozen soil, especially at high latitudes. And this frozen soil has a lot of carbon, has a lot of CO2, and has a lot of methane. As you melt this soil, there is a release of carbon dioxide and methane. As you release that, you increase the warming, you melt more permafrost, and so on. So thanks very much for asking this question. Now, at the moment, this is happening, but is still a minor component. It's only some small regions of the especially Northern Asia and Northern North America that have this problem. Of course, as the warming increases, this will become more and more important. And I think this is one of those tipping points that we don't want to reach, because as you said, once you get this going, there's no way, there's no return. So I think as we are going to exceed some thresholds, this will become more and more important. And at that point, it will be too late, as you said. So that's another reason why we need to avoid reaching that threshold. So this potentially very bad problem, we are not there yet where it has already become a runaway problem. But if the climate system continues to warm, I think this, of course, may be a key contribution to the global warming. I hope I answered your question. Any other questions?
Thank you very much. I think Wafa, she has a question. You can open your mic and ask your question. Wafa.
Hello?
No, I cannot see you.
Filippo, for this lecture. We are so grateful that we met you in person. And I'm Wafayat.
Someday.
I have a simple question. What are the long-term impact on food, especially food security, and how can this impact be mitigated? How can you know?
I did not hear very well. Can you repeat a bit slower? What is the main effect of?
What are the long-term impacts on food
Food production. Yeah.
Yes, special food security and water.
Okay.
But
Yes.
be mitigated.
Okay. Thanks for this question. Okay, I'm not an expert on food, but I can say a few things about this. One of the biggest problems, I think, that we have okay, I don't know if in Sudan you have a lot of irrigated crops, if you use irrigation a lot, or if your crops are mostly using just the rain from the monsoons or something. But there are several potential effects. Of course, in a warmer world, you increase the evapotranspiration, so you increase the need for irrigation. This is actually in many countries a big problem because there's not enough water for that most of the fresh water that is used today is used for agricultural use, not for people's use. So with the warmer temperatures, increase the evapotranspiration loss, we will need more irrigation, and this will increase the need of water. And as I said, this will be a big problem. In Sudan, you have irrigation, or you use only natural, from the rain? You don't know this? Well, anyways, the other issue is that climate change might change the seasonality of the rains. For example, the monsoon might kick on later or earlier. There are depends on where the monsoon is. And this can also affect the agricultural production. In general, many studies have shown that as you increase the temperatures, agricultural production will tend to decrease. Sometimes you might have to, because also you have a greater increase in drought. So maybe you have to use more drought-resistant types of crops. But I'm not an expert, so I don't know what types of crops would be better for warmer climate and climate and food that requires more irrigation. I think the main problem would be because food means water. It takes so much water to produce so much food. For example, to produce 1 kilogram of meat, of cow meat, the FAO estimated you need 15,000 liters of water. To produce 1 kilogram of potatoes or some other crops, you need a few hundred liters of water. So maybe you have to change the agriculture and the food production from meat-based to more vegetable-based type of food. There are many actions that can be taken. But it depends really on the specific situation. But as I said before, water is a big, big issue. I think would be the biggest issue of this century, if you ask me. How to solve it? Yeah, that's difficult. You have to, of course, increase the efficiency of water use. In Italy, that's a big problem because we waste a lot of water. We don't have very efficient channels of transporting water. But that's going to be a big issue in this century, I think. Do you have another question?
Thank you, Prof. Go ahead, Budu, picture.
Bodo, I think.
Yes, open your mic, please.
Hello.
Yes.
How do you say your name? Bidur?
My name is Bidur. I'm meteorologist.
Uh-huh.
I'm graduate from University of Bahri in Khartoum, and I'm climate activist. Participate at COP 2028 and COP 16 Riyadh.
Oh, okay.
Okay. I need to question. Maybe maybe don't study the oceans and the sea. It is a separated ecosystem because the ocean should not be studied and separated from the ecosystem.
Can you say again your question? What about the ocean?
I think the climate actions issues because don't study the oceans and the sea. It is a separated ecosystem from the ecosystem.
Oh, the ocean ecosystem.
Yeah, because in ocean and in the sea, it is 19 interactions.
Yeah, I'm not sure I understand the question, but the ocean cannot be studied separately because it's very much coupled to the atmosphere. So if you change the ocean, you change the atmosphere.
I see. I say 25 emission of the carbon dioxide absorbed by the ocean and the sea.
Yeah. So you're talking
Yeah.
about the ocean.
Yeah, that is the big emissions.
Yeah. Okay, that's a big issue actually because
Yeah.
one of the issues is that the oceans may be decreasing its effectiveness to absorb the CO2, and that's a problem. And also, some people think of some ideas to use the oceans as to absorb the ocean through some algae or something like this. I don't know honestly a lot about this. Would increase the iron content of some areas or something like this. But yeah, I think this is an important issue and needs to be considered.
Okay, thank you, Prof. Thank you all the people who asked questions. Actually, we have received many questions on the chat, so I have to go and focus more in the chat now, and then if there is some time, I will come back to the people who want to ask directly. I want also to mention that it's very nice to see the interaction and engagement because those questions are coming from all the range of levels from senior and undergrad up to the researchers. So it's very nice to see this diversity in the questions. Okay, so if you can be a bit straight to the questions because to cover as much as possible, it will be great. So we have a question from...
I have an issue that my computer is, I still can go maybe 10 minutes, something like this.
Okay, great. Then I will just read to you the question and you can answer directly. So we have a question from Al-Bashir Ahmed. He said, what is...
I think Russia has a question.
Okay, Russia, go ahead then. If you want.
I see her in this, in my computer.
Yeah. Russia, go ahead if you have a...
Anyway, do you know El Fatih El Tahir? Professor El Fatih El Tahir.
Do I know what? Sorry?
Professor El Fatih El Tahir. He's from Sudan.
Al Fatih
El Tahir. Okay. Hold on a second. I need to plug in my computer. Wait just 1 minute, okay?
Okay, sure.
I will be right back.
Okay.
دكتور أبو بكر.
Yes.
بروفيسور الفاتح الطاهر هو دكتور في MIT بتاع علوم مناخ، هيدرولوجيا ومناخ.
Okay. أي أنا بس ما عرفت الاسم. إذا عايز تعقب على السؤال ممكن تعقب عادي يا ياسر، ما في مشكلة.
That's okay.
I'm okay. So I
Yeah.
asked about Professor El Tahir because I'm a good friend with him. So but he's a hydrologist at MIT.
Yes, yes. We have some people here, they know him.
Okay. So Rasha, go ahead with
Rasha, go ahead.
Hi, Professor.
Yes, please introduce yourself and go ahead with the question.
I'm Rasha, a student about to graduate from the Mechatronics Engineering Department. Thank you for your time and effort. In recent time, due to the country's circumstances, particularly solar panel. Yeah.
Your voice is breaking, Rasha.
Isn't clear?
Try again, one time.
Okay.
Okay, you can, okay. Go ahead, Rasha.
We can't hear you now.
Okay, you can hear me now?
Yes.
Yes, yes.
Okay. Many people have turned to renewable energy, particularly solar panels, as you mentioned. However, most of these systems are set up without proper technical oversight. Could this lack of supervision lead to long-term inefficiencies or even turn to this system into electronic waste rather than sustainable solutions? And can theoretical physics inspire practical solutions?
Your voice is still breaking, Rasha.
Rasha, I will have to ask you to write down your question, and then it's just to.
I understand the question, Professor. May I have deliver the question to you?
Sure.
Yeah, she was asking if there the solar panel waste is gonna make a huge impact as in the environment as well as the climate, because she is asking is there a rather or other solution to embrace the renewable energy technology to yeah.
I don't. Okay. Well, first, I don't think the solar panels have this huge impact because you don't really need huge surfaces. Solar panels. Also, I think there are some technologies to have crops underneath the solar panels. And in fact,
yes,
there is less evaporation loss. I don't think they have a big effect on the environment. But in terms of other solutions, you mean with solar panels or? I mean, of course, the wind energy. There is.
Yeah. In the other contexts of renewable energy,
there are many different solutions, but you have to see for Sudan what is the best option. For example, I don't know if you have areas with good wind.
We have in Dongola state. There is studies. There are wind turbines in Dongola. I believe it has been our center was the main research institute for the project, a consultant for the project. We have done some wind studies in Sudan, and yeah, I can answer directly the question that been questioned by Russia, maybe in the chat, so we can move along.
You are not expert on energy, but I am.
Yeah, thank you.
That would be appreciated. Yes, thank you. Okay, so we will carry up, and please, Prof, tell me when you want to stop. So we have a question from Al-Bashir, Ahmed Dr. Bashir.
Let's say another 5 minutes, maybe I can take another couple of questions.
Okay, great. So he asked, what is the difference between climate change and climate variability?
Okay, when we talk about climate change in the context that I've talked about, we imply anthropogenic climate change. The climate change due to human activities, so emissions of CO2, for example, from the body. Climate variability is natural climate variability, so it does not imply that this is caused by human activity. For example, El Nino is a natural thing. Climate change again is anthropogenic. In this context, huh?
Okay, thank you. We have another question from Wisala Zain. She asked, what precaution and measure are being taken by climate experts to address the phenomenon of glacier melting? I don't know if I said it correctly.
Glacier melting. Okay, I mean, the scientists are only studying the phenomenon. I don't think there is much you can do to save the glaciers. If the temperatures go up, the glaciers are going to melt. It's not like you uncovered them with something. At least as far as I know. Let me add something on this, because glacier melting is it's probably the problem that scientists are most worried about. One reason is that the way the cryosphere reacts to change in temperature is very fast. So this can lead to very strong and fast feedbacks. The example I gave you about Greenland ice melt is very important, because Greenland ice is now melting at a rate much faster than we expected maybe 20 years ago. And there are several reasons. Some are due to the dynamics of ice. Also, the ice is darker because of the pollution. So it's darker, it absorbs solar radiation, so it melts faster. But anyways, the melting of Greenland ice is one of these runaway effects. Once you exceed some thresholds, you start exposing the soil, so you kick on the feedback and so on, and it's very difficult to stop it. Now, it turns out that this affects directly the ocean circulation, because the oceans, there is a deep circulation that connects all the oceans, called thermohaline circulation. And the engine for the circulation is the production of very heavy salty water in the North Atlantic. When you produce Arctic ice, what is left behind, because ice is fresh water, it's not salty water. So what's left behind is relatively salty water. If you decrease the production of Arctic ice, and if you melt a lot of, okay, when you produce Arctic ice, what's left behind is salty water, so very heavy water. This water goes into the bottom of the Atlantic Ocean, goes to the other oceans, it warms up, goes up in the surface, and it goes back to the Atlantic. And for example, in the Atlantic, it creates the Gulf Stream, which affects the European. Now, if you don't produce any more Arctic ice, which is what's happening now, if you melt a lot of fresh water from Greenland, then you stop this engine. And if you stop this engine, it changes the whole circulation of the ocean. It changes the whole climate system. Now, people thought that this might happen in 100 years and so on, but there is a very recent study from Nature, maybe 2 or 3 months ago. They put some new ice model in the climate model, which suggests that this may happen much sooner. Now they're talking possibly in 30 to 70 years. So you guys can think actually, maybe not me, but and if this happens, this will mean a big changes. So scientists are studying the cryospheric response. The glacier is very hard because potentially this can be the biggest factor in the global. If you can do something about it, the only thing is to reduce the emissions, to do the mitigation options as in the Paris Agreement. I don't think you can stop it like in some technology. I think.
Okay, thank you, Prof. I think that's enough for now. We have so many questions. If it's possible, we can redirect them to you in the chat in the coming days when you have time, and if that's possible.
We can do by email or something like that.
Okay. Okay, back to you, Ibtihal, if you are here. Otherwise, I can just conclude.
Let me say hi to everyone and good luck with your workshop and with your studies. And if you come to ICTP, maybe some of you have already been.
Yes.
I hope to see you there again.
Thank you. Thanks to you very much, Prof. And thanks all the participants.
It's our pleasure to have this great meeting with you, and thank you to give us your great valuable time. And also we have a good big thanks also for Natasha to being with us today. So at the end we want to have a group picture and then we will end the lecture. So please, all of you, open your camera and be ready.
Okay, we are taking the photos now. This is the first page, the second page, the third page.
Many people.
Yes, so many people. Thank you all. I'm done if they have.
Thank you.
Okay. Thank you all of you, and
Please send me these
we
pictures.
hope we meet you again, Dr. Natasha and Prof. Filippo, in another meeting. And thank you for all our participation. See you next time, and Assalamu alaikum wa rahmatullah.
Thank you very much.
Thank
Okay.
you.
Bye-bye.
Thank you, Filippo.
Bye.
Bye.
Bye, Natasha.